Okay. Thank you and good evening. I'm Nicolo Masi from Bologna University, and today I would like to talk about this study, the study of the local interstellar spectra of cosmic ray up to nickel with the GALPROP-HELMOD framework, and showing some hints of excesses, especially at low energies. Okay, so do you see the slide? It is at the, yeah.
We see it.
Yeah. You know that thanks to recent AMS2 measurements, we can now constrain cosmic ray propagation and production at the percent level. And all AMS2 data published until now can be fitted in, we can see a combined framework using GALPROP and HELMOD. You know that GALPROP is for galactic propagation, whereas HELMOD is a realistic framework for heliosphere propagation. And this can be done using a very single model, which is basically capable of reproducing all primary and secondary spectra at the same time. And we will see, you see the references if you are interested. And we produced these 28 local interstellar spectra using the main data sets from low energy Voyager 1, ACE, CRIS, and so on to AMS, CREAM, and very high energy data such as Nucleon, CALID, and DAMPE. So basically, these spectra are from 10 MeV per nucleon up to a few hundred TeV per nucleon. And this represents obviously a good forecasting tool for the astroparticle and solar physics. Well, the approach is quite simple. It's a Monte Carlo Markov chain approach interface, which is an interface to GALPROP developed here in Bologna. The solar modulation is made using HELMOD, as I said before, which is developed in Milano. And the experimental observable using this study are basically all the primary species published by AMS, including the boron over carbon ratio. You see here we can say the MCMC matrix, which shows the main 5 propagation parameters: the diffusions one, the halo thickness, the convection gradient, and the Alphen velocity. And this approach guarantee, we can say, a 1 order of magnitude of improvement for fundamental parameters with respect to the before AMS2 era. And you see that the model confirms its prediction capability for all AMS2 high precision species with a single set. You see here the dashed lines are the local interstellar spectra, whereas the red lines on the data are the modulated spectra. And you see a good agreement for both primary and secondary species. Thanks to this precise model, we also study, we can say, the injection versus propagation scenarios. I mean, we study at high energy, the hardening above 300 gigavolt. And you see on the left, these two scenarios for secondary species, and on the right for carbon and oxygen with injection, I mean, basically hardening at sources, so I mean in the supernova explosion, whereas for propagation, I mean a break in the diffusion features of the galaxy. So we cannot say something definitive, but basically both the models can be tested using AMS2 data. And if you're interested to forecast, we can say species which were not published, already published by AMS, we used HIAO, basically because AMS and HIAO normalization coincide the percent level in this very region we studied, basically from 2.6 to 10.6 gigavolt per nucleon. So we use this to forecast not published data. And for what concerns the low energy part of the analysis, we are also able to reproduce Voyager 1 data outside the heliosphere, so in the very interstellar space. You see all of the species up to nickel divided into primary, intermediate, and secondary species. And if you're interested, you can find all this stuff on our website, providing numerical lists, formulas, and plots. And obviously, all these spectra will be further fine-tuned and updated on the website using AMS-O2 measurements. But some cosmic ray ions, in principle, still requires the injection of some primary component in some very peculiar rigidity windows. So I'm talking about the hints of some excess, especially in lithium, iron, fluorine, and aluminum. Starting from lithium, you see on the left the plots and the feeds using a pure secondary lithium spectrum and a primary plus secondary lithium spectrum. And you see there is a 25% lithium defect, so you have to enhance the lithium of 25% to catch AMS-O2 data. And at the examination of the lithium isotope production from carbon and oxygen show that the main reaction channels are already well constrained. So basically, such an error would correspond to only 20% error would correspond only to a 2-3% correction in the spectrum. So it's rather unlikely that these cross-section are all biasing in the very same direction to produce this 25% excess. And so we try to describe this excess using the so-called Cameron-Fowler mechanism to produce lithium-7 in the intermediate mass AGB, SARS, and NOVA, which is represented basically by an alpha capture, a transport of the produced beryllium, and then a decay into lithium-7. And in fact, the observation of blue shifted desorption lines of beryllium-7 in the spectrum of some nova, such as this one, B339, Bell, about 50 days after the explosion is basically the first evidence of this mechanism, and then consequent observation of other stars also revealed this presence. So for what concerns this excess, we can say that primary lithium from new stars is mandatory to explain MS2 measurements. For what concerns iron, the situation is different, and we focus on the low energy part because of the large fragmentation cross-section and ionization energy losses. You know that most of cosmic ray iron at low energy is quite local. And the analysis you see on the right of AMS-O2 spectrum together with Voyager, ACE-GRIS, EAO, and other data set reveals an unexpected necessity to introduce a bump in the iron spectrum around 1.3 gigavolt here. And you can see clearly here, for example, in this important iron to primary ratio, iron to silicon and iron over oxygen on the bottom. And you see here that if you catch AMS2 data in red, you have to produce a bump to catch again ACE and Voyager. So these hints of excess fits well with recent discovery, for example, of radioactive iron 60 deposits in ocean sediments, lunar regoliths, and many other observations. Such deposit can be made basically by supernova explosion in the solar neighborhood. And in fact, recent observation of iron 60 by ACE-GRIS spacecraft imply that these low energy cosmic rays from the most recent supernova could be still around. Well, it is hard to establish the exact number of supernova events and the exact timings, but we have several candidates. So there could be several events during the last 10 mega years at distance up to 100 parsecs, and most likely, for example, the Tucano Horologium stellar group. You saw that these hints of new physics at low energy can harbor some key features to describe, we can say, our local bubble. And for what concerns fluorine, you see here the producer secondary spectrum on the left, renormalized fluorine spectrum on AMS2 data at the center, and secondary plus primary fluorine. And I'm going to explain, well, to catch AMS2 data, we perform an overall normalization of about 0.9 due to possible errors in the production cross-section, which is the cross-section basically constant in this very rigidity window. So after the renormalization on AMS2, we saw a remaining excess below 10 gigavolt, which is treated as a primary component. And in fact, this primary component can be clearly seen in AMS2 data, for example, in this fluorine over silicon ratio. You see on the center the rescaled ratio. And well, the origin of cosmic fluorine, basically from nitrogen, is still not well constrained. We have many candidates. The main astrophysical sources are thought to be supernova type 2, Wolf-Rayet stars, and again, AGB stars. And in principle, they could be all important at different stages of chemical evolution of the galaxy. So this could be something new. And for what concerns aluminum, a very recent spectra published by AMS, you see on the left the prediction for the aluminum, which shows this underestimation, this low energy part, and then on the right, the you can say default spectrum plus an excess fitted on AMS2. And there is, in principle, no viable reason of why this aluminum injection spectrum in this very region from 2 to 10 gigavolt should be different from its neighbors in the silicon group, which were well known. So you see, how can we explain, for example, this fine feature in this very species, the aluminum? Well, you see that this feature is still present in the ratios. As for iron and fluorine, you see here, for example, the aluminum over silicon in the upper part of the slide without signal at the bottom with this additional signal. And it can be clearly seen that we have the necessity to introduce this excess also in aluminum. So basically, we study the physical reason for this excess, which can be, for example, an incorrect spectrum of the progenitor of the silicon, or some errors in elastic cross-section, or in the production of the main isotopes 26 and 27, or even additional local components. And without entering into details, it's simple to show that the first three hardly account for such an excess, whereas we have candidates for aluminum excess, for example, from observation of the distribution of the galactic 1.8 MeV gamma ray emission from the decay of the unstable isotope aluminum-26. We can individuate some potential sources, again, AGB stars, collapsed supernova, and Wolf-Rayet. And the source of additional aluminum could be, in principle, simultaneously also the source of other rare isotopes, such as lithium and fluorines. And in fact, it has been shown in literature that Wolf-Rayet stars were already good to explain the observed anomalous neon and iron ratio and so on, and all isotopic ratios measured by ACE are consistent with 20% of Wolf-Rayet material mixed with an 80% of solar system composition. So since this Wolf-Rayet star are found in this OB association, well, they are likely sources of a substantial fraction and additional fraction of low energy cosmic rays. One candidate could be, for example, the Scorpius Centaurus, which is located about 400 light years from the sun. And concluding, for what concerns instead the sodium, from one of the latest measurements by AMSO2. Well, in sodium, we found no excess, and this is quite interesting because wolframite, for example, do not seem to be a significant source of sodium. So this is another proof of this treatment of hints of excesses. And to conclude, so the analysis of nuclei by AMSO2 in this GALPROP-HELMOD framework, together with Voyager, EGAO, and ACE, and many other data sets, provide, we can say, up-to-date local interstellar spectra up to Z equal 28. And aluminum, fluorine, lithium, and iron show significant excess in some peculiar rigidity windows, which is mostly likely local new sources, which have to introduce and which are capable of produce cosmic rays. The wolframite hypothesis, as I told, it could be also consistent with the observed excess of lithium, fluorine, and aluminum, whereas for iron, the excess should be connected with a past supernova activity in our local bubble. The absence of a corresponding excess in sodium supports, as I said, this hypothesis. And so the take-home message is that the exploration of this fine feature of cosmic ray species, thanks to a realistic description of solar and galactic propagation, has just begun, and these features harbor the key to understand our local environment and the history of formation of our solar system.